Swayam Prabha. Digital India. Educated India.
Welcome to lecture 37 on time series modeling and forecasting. In the last lecture, we discussed the causal analysis of multivariate time series. Suppose you have more than one time series and those time series are somehow interrelated with each other, and the time series are stationary and invertible, then you can establish causal relationships between different time series. Now, suppose these time series are non-stationary, or particularly the non-stationarity is due to the presence of unit root. So, suppose you have two time series or more than two time series which have unit root. The question is it possible to establish some kind of relationship between these non-stationary time series or these I1 processes? Obviously, for running the regression, you require finite mean, finite variance, etc., these kind of assumptions. For causality analysis also, you require stationarity and invertibility assumption. And if your time series has unit root, or the set of time series has unit root, and somehow you believe that these time series are interrelated with each other, then the application of some regression techniques is definitely questionable. The inferences drawn after using the regression technique, usual regression technique, may not be reliable, because your time series are violating the assumptions on which the regression is based. Then again the question is how to proceed. Or suppose you run the regression between these non-stationary time series having unit root, then will the results be valid? Or suppose to make these time series stationary, you take first differences. So, suppose you have two time series x t and y t, both have one unit root, so both are I1 processes. You take difference of both the time series and then you run the regression. Now, these two time series satisfy the assumption of regression, both are stationary. Then how is it going to affect your results? Although theoretically you can run the regression, but whether that regression will serve your purpose or not, this is again questionable. So, in this lecture I will discuss all these issues. How to establish relationship between I1 processes and when to establish. Means it may be possible that you have two I1 processes and establishing some kind of relationship between these two I1 processes may not be possible. So, when and how to establish relationship between two I1 processes or more than two I1 processes. So, this will be the subject matter of this lecture. So, basically handling this kind of techniques or establishing the relationships between I1 processes is the subject matter of co-integration analysis. So, I will discuss the co-integration analysis in this lecture. Now, first we consider spurious regression. So, as I mentioned, modeling of two or more time series using traditional regression methods require all variables to be I0, means the variables involved in the regression should be stationary, so that the variables have finite mean and finite variance. Now, do the statistical results of regression hold if some or all of the variables are I1? Now, this is a question. Suppose you have two time series which are I1 processes, and you run the regression between two time series. Obviously, for the given data set, you can always run the regression. It does not matter whether the results are valid or not, but you can obtain least square estimators, etc. So, you can run the regression. So, then the question is, do the statistical results have some validity or not? Or do the statistical results make some sense if you are running regression between I1 processes? So, let us take a simulated data set, and with the help of simulated data set example, we illustrate all these things. What are the problems one may face when regressors are I1? So, we consider this example. So, we consider two independent and I1 processes x t and y t generated by x t equal to x t minus 1 plus v t. V t is a white noise process having mean 0, variance 1. So, this will give you the first time series T s 1 say. Again, the second time series is also an I1 process, y t equal to y t minus 1 plus u t. Again, u t is a white noise process having mean 0 and variance 1, and you get the second time series T s 2. So, notice that both x t and y t are random walk models or I1 processes. So, both are non-stationary. However, if you take first difference of x t or first difference of y t, then the processes become stationary. And then the two time series are independently drawn. X t and y t are independently drawn. So, what you expect? We expect that the regression coefficient is insignificant, because x t and y t are uncorrelated. We expect that the squared correlation r square is very low between x t and y t. So, suppose we draw 10,000 observations from each of these series, then we have plotted these observations. This is the graph of observations from the first time series, and this is the graph of observations from the second time series. And just a visual inspection shows that the labels of the two series are negatively related, means this time series is decreasing and this one is increasing. So, this has decreasing pattern and this has increasing pattern, and if you calculate the correlation coefficient, then the two series appears to be negatively correlated. Now, we run the regression of y on x, say. Then we get the following results. We get intercept term here, which is 27.91. Then the slope coefficient corresponding to x is minus 1.2. So, the slope coefficient is negative. This is what we expect also, because from the visual inspection of graphs of two time series, it appears that the two series are negatively related. As one increases, the other one decreases. Then we have obtained the standard errors of these estimates, the t values also, the p values also. P values are very low. Then residual standard error is 35.82, multiple r square is 0.5655 and adjusted r square is 0.5654. Then the f statistic is given here and this is the p value. Now, you observe that the estimated slope coefficient is negative and r square is moderate. It is around 0.5655. So, this is moderate, not very low. So, on one hand we have drawn the two series independently. So, we expect no relationship between x and y. Still r square is moderate. So, these statistics are representative of the spurious regression, as the two time series are independently drawn. So, this kind of regression is called the spurious regression. And this regression is actually misleading. Misleading in the sense that the two series are independent, but still it appears that the two series are related with each other. Now, we take another example. You have two processes x t and y t, and we generate x t by x t equal to 0.6 I t plus V t. V t follows a white noise process 0 1, then y t is equal to I t plus u t. Again u t follows a white noise process. So, I t is involved in both x t and y t. Then we generate I t by I t equal to I t minus 1 plus W t, again W t is a white noise process. So, this I t is actually an I 1 process. So, I t is a non-stationary process, it is a random walk, and I t is incorporated in both x t and y t. In generating x t we are using I t, in generating y t we are also using I t. So, you can say the processes x t and y t involve common stochastic trend or I 1 process I t in them. So, both x t and y t involve this process I t, which is a stochastic trend. Then again we have generated 10,000 observations from each of these series, and these are their plots. And these plots indicate that the two processes are highly positively related. Just by looking at these graphs, you can easily see that it appears that the two processes are positively related and very highly positively related. Again, we run a regression of y t on x t, and these are the results. We get estimate of intercept term here 0.3212. The slope coefficient is 1.6564. These are the standard errors. Then we have t values, corresponding p values also. Then residual standard error is 1.933 and the degrees of freedoms are 998. Multiple r square is 0.9932 and adjusted r square is also 0.9932. So, approximately these two are same. So, the r square is very high, it is almost equal to 1, very close to 1. Then the f statistic is also very high, p value is very low. So, the regression results are highly significant with high value of r square. So, results are very nice, but since we have already run the regression between two I1 processes and we got spurious regression results. So, here also one may suspect that he is getting all these nice results because both the processes involve a process I t which is I1 process. But on the other hand, it may be possible that you are getting such nice results because both the processes have a common stochastic trend. I1 is involved in x t as well as in y t. So, both the processes have a common stochastic trend. Now, suppose you suspect these results and then you run regression by making x t and y t stationary. Say you take first difference of x t, you take first difference of y t, then x t and y t become stationary, and then you run the regression. So, since both y t and x t are I1 processes, to remove the stochastic trend, we take the first difference and then we run the regression between delta y t and delta x t. Now, these are the plots of first differences, and it looks that these plots are just like a purely random process, but as such just looking at these plots you can't say much. So, again we run regression of y on x. So, we get the intercept term which is quite low here. The regression coefficient is 0.2571. These are the standard errors, then t values, plus p values, these are the p values. Then we have got residual standard error triple R square is 0.053, and similarly we have also obtained adjusted R square, which is also approximately equal to 0.053, and then you have this F star strip. Now, this regression has very low value of R square. So, after taking the first difference, the results are still doubtful. It has very low value of R square. Now, you observe one thing. If you take y t minus 1 upon 0.6 x t, then your y t is I t plus u t and x t is 0.6 I t plus v t. So, if you divide x t by 0.6, you get I t plus 1 upon 0.6 v t, and then if you take the difference y t minus 1 upon 0.6 x t, then you are able to remove this common stochastic trend I t. So, y t minus 0.6 inverse x t is equal to say u t star, where u t star is equal to u t minus 0.6 inverse v t. And since both u t and v t are white noise processes, both have mean 0 and variance 1. So, the mean of u t star is also 0, and the variance is variance of u t, which is 1, plus you have 1 upon 0.6 square into variance of v t, which is 1. So, variance of u t star is 1 plus 0.6 to the power minus 2. So, although both x t and y t are I 1 processes, this combination y t minus 0.6 inverse x t is a stationary process. Or if you define this vector beta equal to 1 minus 0.6 inverse transpose, then beta transpose y t x t, this belongs to I 0 process. So, there exists a vector beta such that beta transpose y t x t is a stationary I 0 process. Both y t and x t involve I 1 process I t, but if you take the linear combination or there exists a vector beta such that beta transpose y t x t is I 0 process. Now, such kind of processes are called co-integrated processes. The original processes are I 1, but you are able to find a linear combination, a linear function of y t and x t, beta transpose y t x t, which is I 0. So, such kind of processes are co-integrated processes, and this vector beta is called the co-integration factor. Now, it is important to develop statistical tools suited for capturing the relations between non-stationary time series properly. So, from the previous example, we observe that it is possible to establish relationship between non-stationary processes. We also observe that since there exists a vector beta such that beta transpose x t y t is a stationary process. So, although the original processes are non-stationary, it is possible to get such kind of linear transformation or such kind of linear combination of y t and x t, which is a stationary process. So, actually this provides you some hint or some idea of how to capture the relations between non-stationary time series properly. And you can easily see the reason why you are able to find such a vector beta. You get such a vector beta because both the processes have a common stochastic trend. Now, suppose the first process has some stochastic trend and the second process has some other stochastic trend. Say x t has a stochastic trend I t and y t has a stochastic trend I t star, say. So, suppose x t is equal to 0.6 I t plus u t and y t is equal to I t star plus v t. So, these two stochastic trends are different. Then you will not be able to find such kind of linear combination or such a vector beta for which beta transpose x t y t is I 0. No, you will not be able to find such kind of vector. So, the only reason is both the processes have a common stochastic trend. So, that is very important for co-integration analysis. So, to overcome spurious relations problem, instead of using the original series, the series should be transformed so that they can be considered as realizations of weakly stationary processes. So, you need some kind of transformation. Since the original series are non-stationary, if you are able to transform the series in such a manner that the resulting model has only weakly stationary processes involved in it, then you may be able to use usual regression techniques. So, in the previous example, if you take this transformation beta transpose y t x t, then it leads to the stationary process, which can be estimated using usual statistical techniques. Now, we consider causal analysis for non-stationary processes. So, we already discussed in previous lecture different causality tests, and you know that those causality tests assume that the underlying processes y t is stationary. Now, suppose the processes have unit root, then this existence of unit root stops you from using traditional asymptotic inference, or the results based on traditional asymptotic inference might be invalid, and this is because of existence of unit root. Then we already discussed that if it is possible for you to transform your model in such a way that all the variables involved are I 0 or stationary, then you may be able to use the standard regression techniques. This error correction representation of VARP process provides you a way out. So, suppose you have vector autoregressive process of order p, y t equal to delta plus a 1 y t minus 1 plus a 2 y t minus 2 so on plus a p y t minus p plus u t. Then one representation which you have studied is this MA representation. You can write y t equal to A inverse L delta plus A inverse L u t, where this A inverse delta is equal to mu, and then you have A inverse L u t. So, you get a moving average representation of infinite order here, and you can write it as mu plus B L u t, where B L is equal to I plus summation j equal to 1 to infinity B j L to the power j, and this is equivalent to A inverse L, and B naught is equal to I k. You also know that mu is actually equal to A inverse I delta, because lag of delta is delta. Now, we consider the error correction representation. So, every stationary VR process of order p, say y t equal to this, or you write it as I minus A 1 L minus A 2 L square so on minus A p L to the power p y t equal to delta plus u t. This can be written as A p minus 1 star L delta y t equal to small delta minus A 1 y t minus 1 plus u t, with A p minus 1 star L is equal to I minus A 1 star L so on minus A p minus 1 star L to the power p minus 1. A I star is equal to minus summation j equal to I plus 1 to p A j for all I equal to 1 to p minus 1. So, here you are taking delta y t. So, all the variables or the time series related with all the variables involved are stationary after taking the first difference. And then if this part is also stationary, or if you are able to find a matrix such that A 1 y t minus 1 is stationary, just like the previous example where we got the vector beta such that beta transpose y t x t was stationary. So, if you are able to find such kind of matrix, then this also becomes stationary, this is stationary. So, your model involves all the stationary series. So, you get rid of that non-stationarity problem because of presence of unit root, or because of I 1 processes, or because of stochastic trend. So, we prove this error correction representation now. You observe that A I plus 1 is equal to A I plus 1 star minus A I star, just by the definition of A I star. If you take the difference A I plus 1 star minus A I star, then you get A I plus 1. Then we take A p star equal to 0, and A naught star is equal to minus A 1 plus A 2 so on plus A p. For I equal to 0, you have A naught star. So, summation j equal to 1 to p A j you have here, then you have minus sign here. So, you get this I plus A naught star is I minus A 1 minus A 2 so on minus A p. So, this is equal to A 1 within bracket 1 say. Then we can write I minus A 1 L minus A 2 L square so on minus A p L to the power p as I minus you substitute A 1 equal to A 1 star minus A naught star L minus you write A 2 equal to A 2 star minus A 1 star L square minus so on. You write A p equal to A p star minus A p minus 1 star L to the power p. Notice that this A p star is equal to 0, you have defined here. And then you can write it as, say you take I 1 minus L here, then I plus A naught star, you have this I, you get this I here, then you have taken this term minus L here. So, we will adjust this term later on. Then you have taken I plus A naught star L. So, here you have subtracted L, here you are adding L, and then you have A naught star L, which you get from here plus A naught star L. And then, so suppose you take this term A 2 star minus A 1 star L square minus A 3 star minus A 2 star L cube. Then you collect the term having A 2 star. So, A 2 star L square 1 minus L you get here, and then you adjust this term minus A 1 star L square with the previous term. So, here you have minus A 1 star L, and then you have plus A 1 star L square. So, you get A 1 star L 1 minus L square and so on. So, finally, you get this expression minus summation j equal to 1 to p minus 1 A j star 1 minus L L to the power j. So, you can write the error correction representation of vector autoregressive process given in equation 3 as I 1 minus L plus I plus A naught star L minus summation j equal to 1 to p minus 1 A j star 1 minus L L to the power j y t equal to delta plus u t. Or you take I here, then 1 minus L y t is delta y t minus summation j equal to 1 to p minus 1 A j star, you have 1 minus L. So, you get delta y t, then you have L to the power j. So, delta y t minus j, and then on the right hand side you get delta minus A I y t minus 1, because A I is equal to I plus A naught star. So, you take this term towards the right hand side, get minus A I y t minus 1, because you have L here. So, L y t is y t minus 1 plus u t, and then we write this term equal to A p minus 1 star L delta y t equal to small delta minus A I y t minus 1 plus u t. You can also write this 5 as delta y t equal to small delta minus a I y t minus 1 plus you take these terms towards the right hand side. So, you get summation j equal to 1 to p minus 1 a j star delta y t minus j plus u t. So, all the components of y t are I 1 variables. So, after taking the first difference, each component say delta y t minus 1, so on delta y t minus p plus 1 is stationary or it is I 0 process. For each component of this y t minus 1 is I 1. So, all the variables become stationary only when you are able to find some matrix A I such that A I y t minus 1 is stationary. Now, this delta y t is I 0 process. So, as t increases, this delta y t and u t approach to 0. Delta y t is a stationary process and it has mean 0. So, in the long run it approaches to its mean. Further, u t is a white noise process, then u t also approaches to 0 as t increases. Then the process approaches to the equilibrium state delta minus pi y t minus 1 equal to 0, where pi is equal to a I. Because in equation 6, this term goes to 0, this term goes to 0, this term goes to 0. So, you get this equilibrium state delta minus a I y t minus 1, or you can say that this term represents the long run relationship between the variables of the time series. And these are the terms involving delta are short term corrections, or these give you the short term relationship. Now, this is the beauty of error correction representation. The error correction representation decomposes the process into two parts: the long run relationship or the long run equilibrium and the short term relationship or short term corrections. Then this pi represents the matrix of the long run equilibrium relations and can be estimated directly in the framework of a linear model. So, you can apply the tools of the linear model like method of least square for estimating pi, provided such a pi exists. Now, if such a matrix pi exists, so that pi y t or pi y t minus 1, whatever you write, this is I 0, then we say that the vector y t or the processes involved in this vector process y t are co-integrated. I will come to the formal definition of co-integration later on, but if such a matrix exists which makes pi y t I 0 process, then we say that these processes involved in y t are co-integrated. Then the Grangers representation theorem states that the entries of the I 1 vector y t are co-integrated if and only if they have an error correction representation. So, if y t has an error correction representation, then you can say that the entries of y t are co-integrated. Now, you can consider this general dynamic model of a single equation and one explanatory variable which is assumed to be exogenous. So, you have alpha p L y t equal to delta plus beta q L x t plus u t. In the long run equilibrium, y t minus 1, so on y t minus v, all these tend to y bar. Similarly, x t minus 1, so on, these approach to x bar and u t approaches to 0. Thus, we get the long run equilibrium, say alpha p 1 y bar equal to delta beta q 1 x bar. So, this is the long run equilibrium, and why you get alpha p 1 here? Because L y bar is equal to y bar. So, alpha p L y bar is equal to alpha p 1 y bar. So, you get this long run equilibrium, and then you can write it as y bar equal to delta upon alpha p 1 plus beta q upon alpha p 1 x bar, and then you can write it as mu plus beta x bar, where mu is equal to delta upon alpha p 1 and beta is beta q 1 upon alpha p 1. So, you get this kind of linear relationship between y bar and x bar. Now, if y and x are weakly stationary or non-stationary, but co-integrated, then we can get the following alternative representation or error correction representation for the processes. Say alpha p minus 1 star L 1 minus L y t is equal to delta plus beta q minus 1 star L 1 minus L x t minus gamma naught y t minus 1 plus gamma 1 x t minus 1 plus u t. Again, alpha p minus 1 star L is equal to 1 minus alpha 1 star, so on alpha p minus 1 star L to the power p minus 1, alpha I star is equal to minus summation j equal to I plus 1 to p alpha j, and beta q minus 1 star L is equal to 1 minus beta 1 star L, so on minus beta q minus 1 star L to the power q minus 1. Beta I star is defined here. Gamma naught is equal to alpha p 1 and gamma 1 is equal to beta q 1. Now, in equilibrium, delta y t and delta x t tend to 0, then u t is also equal to 0. So, y t is equal to y bar, x t equal to x bar, and then your relation reduces to this minus gamma naught y bar plus delta plus gamma 1 x bar equal to 0, or you can write it as minus alpha p 1 y bar plus delta plus beta q 1 x bar equal to 0, because gamma naught is equal to alpha p 1 and gamma 1 is equal to beta q 1. So, this representation 5 has long run equilibrium. So, using this error correction representation, these short term and long run effects are separated and can be directly estimated. You can directly estimate these short term and long run effects. So, all this is short run effect, this gives you long run effect, and this part also gives you short run effect or short term corrections. Now, we define co-integration. When linear combination of two I 1 processes become an I 0 process, then these two series are said to be co-integrated. Then why do we care about co-integration? Why we need co-integration? Because co-integration implies existence of long run equilibrium. Then co-integration implies common stochastic trend. The two processes have common stochastic trend, then they are co-integrated. Then with co-integration we can separate short and long run relationship among variables. So, this we have already also observed that we are able to separate these short and long run relationships among variables. We just write the process in error correction form, and then you can separate short and long run relationship. Then co-integration can be used to improve long run forecast accurately. Co-integration implies restrictions on the parameters, and the proper accounting of these restrictions could improve estimation efficiency. So, you require certain restrictions on the parameters of the process, and if you take care of these restrictions, then your estimation efficiency also increases. So, now we define the co-integration. The elements of a k dimensional vector y are co-integrated of order d c, denoted as y follows c I d c, co-integration process of order d c. If all elements of y are I d, so original process is I d, and there exists at least one non-trivial linear combination z of these variables, which is I d minus c. So, the original process is I d, but after taking this linear combination it becomes integrated of order d minus c, where d is greater than or equal to c and c is greater than 0 holds. So, beta transpose y t is equal to z t, say, then this follows I d minus c process. This beta is termed as co-integration vector. Then the number of linearly independent co-integration vectors is known as co-integration rank R. So, you can find many co-integration vectors. Then you only consider the number of linearly independent co-integration vectors, that is called the co-integration rank. So, suppose we form the co-integration matrix by co-integration vectors as the columns with beta transpose y t equal to z t. So, you consider all the co-integration vectors in the column of B. So, you get this matrix B, then B transpose y t is equal to z t, and if co-integration rank is R, if number of linearly independent columns is R, then rank of B is R. So, this is the co-integration rank. So, in this lecture we have discussed if you run direct regression between two I1 variables, it may lead to misleading results. Such kind of regression leading to misleading results is called spurious regression. Now, we also looked that if both the processes have some common stochastic trend, then it may be possible to modify your process and run the usual regression techniques. Then we consider the error correction representation of the vector autoregressive process, and we observe that it is able to decompose the process into long term equilibrium and short term corrections. Then we have defined the co-integration. In the next lecture, I will consider the co-integration in more detail. Thank you.
Hello, good morning everybody. I am Raghunandan Sengupta. So, I will just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So, what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it say for example derivative pricing, be it in the area of say for example portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance as I mentioned. Now, we all know that in 1997 the Nobel Prize in Economics, so it is basically the Nobel Memorial Prize in Economics was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high-ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also, obviously when there is a huge amount of development. So, obviously due to some regulation errors or something, there has been some pitfalls, which I think is should be a bullet point for people who are really interested to take up quantitative finance, they should be aware. So, consider the financial crisis in 2008 and later on, and we are seeing different banks are failing, different financial institutions are facing a problem, countries are facing a problem like in Europe, in USA. So, what should be done? So, the main thing is that even if you know the technique is best for people who are investors, who are private players, organizations like banks, governments should use these techniques in a very somber manner, such that the application areas of quantitative finance using the techniques which we learned can be utilized in the best possible way to garner the overall the in-depth knowledge a person has in trying to utilize these quantitative techniques in finance. And I am sure that people who have the background, who have the knowledge, who have the sophistication, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.